Okay, I think it's going. All right. So, we left off somewhere around here on page 14. Okay, so if you guys kind of, we're halfway down page 14. You can find where we are. So, what did we talk about? We talked about how to arrange a reduction potentials table experimentally, right? And that's what the lab was all about. So, we can do more with reduction potentials table. We not only just metals, but we can determine the likelihood of other reactions taking place. So, for example, if we have a solution of tin chloride, right, tin chloride, just imagine we have a beaker. So we've got tin ions, you got chloride ions, right? And we are adding to this bromine, diatomic bromine, which remember, bromine is a liquid under standard conditions. So what's going to happen? What reaction will happen if we just dump bromine into a solution? So what we have to do is we have to consider the possibilities, and then we have to figure out which possibilities are likely. So first, let's consider what things that are here can possibly be oxidized. Well, tin is listed twice on your reductions table. Tin 2 can be oxidized to become tin 4. So that is a possibility. Also, chloride can be oxidized to become chlorine. So that is a possibility. Okay? Now, what you're looking at here are oxidation potentials. So the way that you figure out which one of these two oxidations is possible is the one of greater or of more positive value, right? So between these two oxidation potentials, this is the greater oxidation potential. So if there's going to be an oxidation, it's going to be that one. All right, so let's look at the reductions. Tin could be reduced from ion to solid metal. Okay, and so this reduction potential is taken straight off of the chart. Bromine can be reduced to bromide, and that's taken straight off the chart. Now, clearly between these two, the positive reduction potential, like this is the greater reduction potential, so that's the reduction that's going to take place. So by simply listing what can be oxidized, what can be reduced, picking the highest of each category, that tells you what's going to happen. Now, I do need to stress this because this is something people kind of forget. If you're going to write down oxidation potentials, you got to remember to flip them, right? These are not taken straight from the table. These were flipped from the table. Okay, so be careful of that. Whenever you write EOX, make sure that you did the right thing to get that value. So the overall reaction would be your tin 2 positive plus Br2 forms tin 4 plus 2 bromide, right? And then E cell you find the same way we always found it, right? You take EOX plus E red, both of which we have. EOX is going to be negative 0.154. E red is 1.077, so we net out with a positive value. So the voltage here is positive 0.923. So it's spontaneous, it will happen. Okay. So let's talk about a similar situation, similar but slightly different. Let's say we have a piece of iron. When we say a piece of iron, we mean solid, right? Because it's a solid piece. And we plunk it into a beaker that contains these solutions. These, we have ions of potassium, silver, copper, and zinc. The question says, determine which metal ions will be reduced by the iron. And the way that you do this, if you're asking which metal ions will be reduced, what you're really asking is which of these are more easily reduced than iron. And that's pretty easy to do. What you're looking for then is on your reduction potentials chart, which of these have higher reduction potentials than iron? So I'll give you a minute. Just take a glance at your chart. Oh, speaking of which, for your convenience and viewing pleasure, I don't know if you printed this out at home on your own already or not, but hey, here's a copy. What time is it? What do you think? Should I get him one? Oh, I guess you can. Is that what you were doing all this 10 minutes ago when class started? I was looking for fun. All right. So, which of these ions, which of these metals are more easily reduced than iron? More easily reduced meaning higher reduction potential. Which one? Copper, yes. Silver, yes. So do you guys understand what is happening, or what will happen? Once this piece of iron gets plunked in there, what we're going to end up with is the potassium is unaffected, the zinc is unaffected, the piece of iron will have, there's an order to this, by the way. Which one of these will reduce first, silver or copper? It's the one with the greater reduction potential is the first one to be affected. So silver. So what you're going to see is we're going to get accumulation. Okay, so solid silver is going to accumulate on that piece of iron, and you're going to get some oxidation of iron into solution, right? Because it's a redox reaction, right? If something's going to be reduced, something's got to be oxidized. And if the silver ion concentration becomes exhausted, then the next metal will be reduced, which we said was copper. Right? But if, it all depends on how much you have, what the concentration is. So, Ag first, copper next. Okay. So, if you're okay with understanding how to use the relative position on a reductions chart to determine which reductions are taking place, let's talk about a powered cell, an electrolytic cell. Remember from the beginning of this section that an electrolytic cell uses energy. It requires energy to make non-spontaneous reactions happen. An electrolytic cell nothing will happen on its own unless you plug it in and turn it on. Okay, a light bulb is an electrolytic cell. Nothing happens to the light bulb unless you force electrons into it. So, I mentioned the term electroplating. Electroplating is by far one of the most common industrial uses of an electrolytic cell. So it goes something like this. Let's say that my daughter has a My Little Pony figurine, right? And so let's say that she wants it to be gold-plated. Okay. You know how they have like the symbol on the side? Okay. Big eyelashes. Okay. So let's say, looks a little thick there, maybe. Whatever, it's pregnant. Okay. Let's say she wants this to be gold-plated. So here's how I could do that. I will take a piece of gold and I will connect it to a power source. And the power source end, I will clamp it onto the pony. And I need a bunch of other electrolytes, some conductivity, so I'm going to have like a sodium nitrate solution in here. Okay. And all I need to do is send power, and what's going to happen is as this electrolytic cell runs, there's also some gold ions already present in solution because they have to be. So what we're going to observe is gold ions will be reduced, and they will coat the figurine, right, with gold. Now, the gold concentration of ions is going to be depleted the longer this happens. So we need to provide a source of additional ions, and that's why there's a gold bar in solution, because the gold solid will be oxidized and replenish the gold concentration in solution. So we have an oxidation of gold and we have a reduction of gold. This reaction in and of itself will not happen spontaneously, which is why it requires external power. Now, you could substitute that figurine with a spoon, a comb, whatever. A bumper to a 1950s classic car, right? We could use chrome instead of gold, right? I mean, this is the basic tenet of electroplating. It's pretty simple. Electron-wise, in which direction are my electrons flowing? Towards the bar or towards the pony? Well, which reaction do we want happening on the pony? We're putting solid gold onto the pony, right? Which means we need it to be reduced. So electrons have to be sent towards the pony so to reduce the gold ions into solid. And the electrons are being pulled, actively being pulled by the complete circuit of the power so that the gold solid can be oxidized and turn into ions. Okay. This is a fairly typical electroplating setup. Does that make sense here? All right. Nothing too elaborate. Okay. So now let's talk about one step further, electrolysis of water. Now I mentioned electrolysis specifically of water because water is now a participant. Everybody take a look at your potential sheet. All right, your potential sheet. And first off, everybody about 2/3 down, you should all see the reaction that reads 2 moles of water plus 2 moles of electrons forms hydrogen gas plus 2 moles of hydroxide with a negative 0.83 reduction potential. Everyone see that? Okay. That reaction is the reaction for the reduction of water. Now, when I say reduction of water, if we dissect water, and if I asked you, what's the charge of each element in water, or what's the oxidation number of each element in water, I am presuming, after some prodding, you would all be able to tell me that hydrogen is a +1 and oxygen is a -2 in the formula. Right? Remember when we assigned oxidation numbers in formulas? Okay. So when I say reduction of water, I'm really talking about reduction of the element in water that can be reduced. There's two elements. Hydrogen currently has a +1 oxidation state, but hydrogen can go down to a 0 oxidation state by forming diatomic hydrogen. So the reduction is actually the reduction of hydrogen, not of water as a whole, but just hydrogen, the element from water. And the other product is hydroxide, which is the remains of water after hydrogen has been pulled off. So that is where this reaction comes from. And we balance it, right? And after balance, and 2 electrons. And then we get E red to be -0.83 volts. Okay, that is the reduction of water. But water is present in all aqueous solutions. That's why we call solutions aqueous. So if water can be reduced, water can also be oxidized. So if you look up 5 reactions down from the top on your chart, do you see oxygen plus hydrogen ion forms 2 moles of water? That reaction on your chart, here, I'll rewrite it here. So O2 plus 4H plus 4 electrons becoming 2 H2O liquid. This is not the reduction of water. Okay, this shows oxygen combining with hydrogen ion. However, what the pertinent thing about this reaction is that if you flip this and rewrite it backwards, this now exemplifies the oxidation of water. And again, it's not water literally that's being, it's not water that's literally being oxidized. It's an element within water that's being oxidized. So in water, hydrogen is +1, oxygen is -2. Which of these elements can have its charge go up? The hydrogen or the oxygen? Yeah, the oxygen. Oxygen can go from -2 to 0. So it's actually oxygen that is being oxidized. But because your table is written as a reductions table only, this equation had to be wedged in there and turned around. But it's on here for reference because you're going to need it. You're going to need to be able to find what happens when water is oxidized and what happens when water is reduced. Okay? All right. So whenever you have a solution, and whenever you stick 2 electrodes in there and turn the power on, something's going to be oxidized, something's going to be reduced, water among them. So let's examine a copper bromide solution. This is, I need to edit this. This was actually, there's a way to erase the black text on here, right? If I use the white color, is that right? Just learned this. Oh my goodness, that's not what I want to do. That's too big. Copper bromide. That's still too big. Oh no. Oh no. Ah, forget it. In a copper bromide solution, all right, that's what I'm trying to do here. All right, that's still too, that's not narrow enough. There we go. In a water copper bromide solution, copper is reduced. So let's evaluate how we make this decision. So here's the setup. Copper, bromide, water, 2 electrodes, power source. The double line indicates power. Do you guys remember that from, did you guys do E&M last year? No? Okay. So I have these 2 electrodes, and the electrodes don't need to be copper. This is not a voltaic cell, so the electrode that I'm using for copper on both sides, they can both be inert. They can both be graphite. They can both be platinum. They can both be nichrome. All right. So what you need to do for each reaction is write down the things that can be oxidized, the things that can be reduced. So first off, the cathode reaction, or in other words, what can be reduced? Well, we wrote down water. Water can be reduced. So they show the reduction of water. And copper. Copper can be reduced. Between the 2 of these, we have a higher reduction potential of positive 0.339 volts. All right, the reduction potential for copper is greater than the reduction potential for water. So that tells me the copper reduction is going to take place. Okay, so at the anode, remember the anode is where oxidation takes place. So what do we have in solution that can be oxidized? Bromide. Bromide can be oxidized, and its oxidation potential is negative 1.077. Water can be oxidized, and if it is, then we get hydrogen ion, oxygen gas, and the oxidation potential is negative 1.229. So between the 2 of these, the higher oxidation potential is the one that will happen, and thus the overall reaction will be Cu. Technically, you should write these as half reactions first because you might need to balance them. So I'll write them as half reactions. So that's the reduction. This is the oxidation. The number of moles of electrons for both cancel. So that's convenient. So the overall reaction, oh, I should probably write the this potentials as well. So E red, 0.339, E ox, negative 1.077. So overall, and we have an overall cell potential of negative 0.738 volts. What does that negative sign tell you? Non-spontaneous, which is why we are doing this under the electrolytic section, because this wouldn't happen unless you externally power it. Okay, this is one of those things that doesn't really hit home until you do a bunch of examples, so let's do the next one. Okay, I'm going to skip A, let's just jump to B. Aqueous nickel bromide. All right, so aqueous nickel bromide. I got nickel ions, I got bromide ions, I got water. So in order to figure out what's happening, write out your possibilities. I just kind of make 2 columns. That's still too thick. Let's try this. Possible oxidations. In this beaker, what can be oxidized? What can have its charge go up? bromine, right? Bromide can become bromine, right? And so that value we had earlier as it was negative 1.077. What else? Can nickel? What's that? Yeah, water. Right, water. We just spent 10 minutes talking about water. So water can be oxidized. When water is oxidized, we get hydrogen ion, and we get oxygen gas. Anything else? Transition metal elements often have multiple valences, right? So let's check and see if they have put nickel 3 on here. They didn't bother putting it on here. Okay. Well, if they didn't put nickel 3 on here, then that's a sign to you that you're just not going to use nickel 3. All right, so it's not being considered, but in reality, nickel 3 is a possibility, but it's not really going to be one of the ones that happens. Okay, possible reductions. Oh, actually, decision time. Which one of these oxidations is taking place? Bromine. Okay. What are the possible reductions? Is there such thing as bromine with a -2 charge? No. Halogens can only go down to -1. So what else can go down? Nickel. We can reduce nickel. All right, and the potential for that, yeah, negative 0.25. And then water. All right, water can be reduced. All right, so the highest of the reduction category is the nickel. So your overall reaction will be 2 bromide ions plus the nickel ion forming diatomic bromine and nickel solid. And then the cell voltage will be the sum, which is going to be here inherently a negative value. Okay. You guys getting the hang of this? All right. If you dissect it and treat them and do one at a time, do the oxidation and then do the reduction and then add them all together, it's pretty straightforward. Now, here we saw that the electrons canceled when we combine them. Remember that a balanced redox reaction still needs to be balanced, so you would still have to multiply by 2 or 3 or whatever if you need to. But if you do multiply, remember you never multiply the potentials. Right? The potential values are intrinsic, right? It's independent of the amount. So you just use the actual voltages as they are. Okay, let's see. Yeah, we have time. We'll do one more. Let's do the, well, let's just do the next one. Let's do aqueous aluminum fluoride. Actually, I'll let you do it. Take a minute, figure out what's going to happen with aqueous aluminum fluoride. Oh, and then we'll see. So, guys, what are my products? Yeah. Okay. Which is your actual oxidation that's taking place?
Water for both?
Yeah. You have water being oxidized, water being reduced. Your net equation basically will amount to the sum of those. But here's the thing, you got to multiply, right? So overall, you end up with, you know what? I'm going to use the lasso so I don't have to rewrite all this. Okay, and then so here's my oxidation, here's my reduction. The fluoride to become fluorine as an oxidation, the oxidation potential is going to be negative 2.87. All right, so clearly this is our oxidation that's taking place. Our reduction, the reduction of aluminum, was negative 1.66, and the water reduction is the greater of the two, so that's what's going to happen. So notice your electron counts, right? Because redox reactions have to be balanced both in number and in charge. So that means this reaction is going to have to be multiplied by 2, because your loss and electron loss, electron gain must be the same. So overall, your equation ends up being this. Your cell potential ends up being negative 2.06. We get that? All right, good. I mean, you could simplify this too. Like we could actually subtract out, like these two form 4 waters, and we could reduce this, and so that will lead us to this if we simplify, which is fine. I guess technically this is our net equation, okay? But the point is, only water reacted. Okay, so if given a salt solution, you understand how to figure out what the products are once electrolysis takes place. Right? Yes? Break it apart, use the charts. Highest potential in each category dictates what happens. Okay, good. So, let's talk about some physics terms and some calculations. So, joules, we've been calculating joules all year long, right? We've used joules when we talk about caloric energy, thermochemical energy. But joules also, it can be solved for electrically. So the joule is a measure of electrical energy. It's a Coulomb charge over a potential of 1 volt. Or in other words, we can solve for joules by multiplying the coulombs by the potential. Right? So coulombs, remember, that's the charge. And volts is our potential. And J is our energy, joules. Okay? So one single electron has a charge of 1.6 times 10 to the negative 19th coulombs. How many coulombs are there per mole of electrons? Okay, so if I want to solve for how many coulombs there are, if they're telling me that there's 1.6022 times 10 to the negative 19 coulombs per electron, by extension, there are 6.022 times 10 to the 23rd electrons in a mole of electrons. And this gives us 96,485 coulombs per mole of electrons. This is what we call a Faraday. Right? A Faraday is a set value. It's a value. It's the charge per mole of electrons, which is going to be very useful to us. So, if you treat this as an equation, like a 3-variable equation, right? Joules is equal to coulombs times volts, then you could rearrange and you could solve for either the charge or the voltage if given the other two. Now, these equations here are going to be, it's just kind of summarizing what we have here, right? So, right here, these are the same equation. Okay, so what else do we need to know? We need to know what amps are, amperes. Amperes are the rate of electrical charge current. And like a rate, like miles per hour, it's coulombs per second. So because it's involving the time component, we could solve for how much time it takes based on the amperage and the charge. Right? And so this equation for current is reiterated here. So let's apply these terms and see if we understand how to use them. All right, so let's say we have a car battery. Car battery is typically a 12-volt battery. Suppose the battery furnishes a current of 10 amps for 15 minutes. They want to know two things: the number of coulombs and the number of moles of electrons. All right, so the first one, number of coulombs. If they want to know the number of coulombs, they want to know the number of charge, and we know the current and we know the time, we can just set up with the amps and say, all right, well, 10 amps is really 10 coulombs per second. Okay, right? An amp is a coulomb per second, so 10 coulombs per second. And they're saying this runs for 15 minutes. And there's 60 seconds per minute. So that's how we can find the charge that has been dispersed over this time period. So what is that? 9,000? Okay. 9,000 coulombs. All right. The next question is, how many moles of electrons were used? Well, remember that important value I said that's going to come in handy? The green value, the Faraday? Let's use that. So if there's 9,000 coulombs, we just divide by the Faraday to figure out how many moles of electrons. So what's that going to be? Point 0.0933 moles. Okay. You guys good? All right. We found moles by using the Faraday. We were able to find charge by using amperage and the time. How about electrical energy? Electrical energy using the work formula. Guys, the work formula is the same thing as this formula. Okay, so the work, as in the energy, which is then going to be in joules, voltage is your potential, and charge is coulombs. So how much energy is there? How much work can be done? Well, do we have the volts? I didn't calculate the volts. Where am I going to get the volts from? It's given. So 12 volts times 9,000 coulombs. So a volt is a joule per coulomb, in case you're wondering unit-wise how that works out. So 12 times 9,000, 108,000 joules. Okay. Apologize for breezing through this quickly, right? But I am assuming that you guys did a fair amount of energy and work calculations in physics, okay? And it's good. Also, we're recording this, so if you want to watch this again, you can. I'll post the link in Schoology. All right. Lastly, well, not lastly, but anyways, let's solve for the amounts of something that we get during electrolysis. So in reduction of silver, 1 mole of electrons gives 1 mole of silver, meaning this. Very simply stated, if I have 1 mole of silver ions, I need 1 mole of electrons to reduce it. Okay? All right, well, that's not earth-shattering. That's fairly straightforward. So this will enable us to answer the question, how much silver is plated, meaning mass? How much silver is plated if we have a current of 2.6 amps in 1 hour? So we are working with amps, and remember that amps is charge per time, or coulombs per second. So 2.6 coulombs per second. We have 1 hour. An hour is 3,600 seconds. And since I have coulombs, my bridge to get from coulombs to mass to moles is the Faraday. And I know that a mole of electrons is what's needed for a mole of silver. And lastly, a mole of silver weighs 107.9 grams. So we're looking at about 10.5 grams of silver that will be plated if we have enough silver ion and we let this run for 1 hour at a current of 2.6 amps. 10.5 grams of silver is actually, it doesn't sound like a lot, but when you're electroplating, that means you're just coating the surface with the metal, right? You're not making a fully solid piece of silver. It's just you're covering it. Okay. You guys ever hold on to something that's like a plastic toy that's silver, but over time the silverish rubs off, right? So the electroplated silver rubs off, right? Okay. Actually, they wouldn't electroplate toys anymore. I guess that's more so household items. All right. Using that logic, try to figure this out. How long will it take to deposit 0.5 grams of nickel ion onto the cathode if we have a current of 3 amps? We're solving for time now. molar mass is 58.7, in case you're wondering about nickel. So how much time, guys? What do you think?
$548 seconds.
Yep, good. That's what I got. 548 seconds. So to set the problem up, it's just kind of straightforward stoichiometry. Start with 0.5 grams of your nickel. And when I use the molar mass for nickel, it's the same whether it's the ion or the atom. Right? It doesn't really change. Right? So in a mole of nickel, it's going to require 2 moles of electrons. And that's the thing most people will miss here, the fact that there's 2 moles, because it's nickel 2, right? So to reduce it, you need 2 moles of electrons. And then for every mole of electrons, 96,485 coulombs, because that's the Faraday. And then lastly, the amperage is 3 coulombs per second. So run the numbers and you get 548 seconds. Are we okay, guys, solving for either the mass or the time during electrolysis if we're electroplating? Okay. All right, good. All right. How far can we get in 14 minutes? All right. So voltage and free energy are related, right? Since delta G is a measure of useful work, right? So delta G is measured in energy in joules, and joules can be found if we take a product of charge by voltage. So that means that we can use this equation here to solve for the free energy if we know the potential, right? Where N is the number of moles of electrons. In the last problem, N was 2, but in the previous problem, N was 1. It all based on how many moles of electrons are needed for reduction. F is the Faraday constant, and E is the potential. I guess it should be capital E. But anyways, negative NFE is how you solve for G, right? So anytime there's a voltage given, you should be able to solve for delta G. Okay. So we earlier had discussed the relationship between equilibrium constants K and delta G. We said that delta G was equal to negative RT ln K, R being universal gas constant, but remember we were using 0.00831 joules per mole Kelvin. Okay. Kilojoules per mole Kelvin. So if we have 2 things that equal delta G, that means the 2 things are also equal to each other. So we can directly correlate voltage with an equilibrium constant using this equation. Now, there are going to be times, there's different variants of this equation. So this in and of itself can be used directly, but a useful derivation is ln of K multiplied by the potential over 0.0257. This is taking into account that 8.31 joules per mole Kelvin is used for R, and the temperature is 298, and the Faraday is used. However, in your AP formula sheet, what you're going to see is this, and it's just using base 10 instead of base E. And this is actually the form that I would recommend then, because that's what you're going to see on the AP test. So But however, whichever formula you decide to use, it's just kind of a matter of convenience based on the numbers that you currently have in the problem. So they both work. Just kind of, you know, one is partially rearranged for you. So basically what you need to do then is take an equation, find the voltage, find the free energy, and then find the K. So let's do that. So the equation that we're referencing is right here. Chlorine being reduced, bromine being oxidized. So to find E, I need to know the oxidation potential and I need to know the reduction potential. So the reduction potential is easy. That just comes straight off the chart. For bromine, the reduction is 1.07. The oxidation, I'm sorry, I got backwards. Hold on, my mistake. The bromine is being oxidized. So that's negative 1.07. Okay, the reduction, the chlorine, is 1.36. Okay, so .29. Okay. So can we take this voltage and can we find the free energy from it? Yes, we can, because delta G is equal to negative NFE. What is N? How many moles of electrons are being transferred in the reaction between chlorine and bromine? What do you guys think?
2?
Yes, it's 2. If you break this in half, it becomes evident right? N is equal to 2. So, negative 2 times 96,485 coulombs per mole. And the unit, by the way, is on the on N is moles. And then our voltage, we said, was 0.29, which is joules per coulomb. So free energy is negative 55.9 kilojoules per mole. Which we can tell is going to be spontaneous. All right, the last thing then is how do we solve for equilibrium constant? There's a number of ways. You can use either one of the equations I just mentioned, but we'll use the one that put a box around just because we haven't used it yet. All right, so yeah, it's a big number. 6.2 times 10 to, I gotta count these. 1, 2, 3, 4, 5, 6, 7, 8, 9. Which is totally feasible. All right, this is a very, very spontaneous reaction, so expect K to be large. Okay, I think that's about as far as I can go today without having people's heads fall off. So let's recap. And we'll have to pick up the last bit on the next class day. Let's recap. All right, so in an electrolytic, wait, is that where we started? No, we started here. In order to figure out what reaction will happen, you have to look at what all the possible oxidations, what all the possible reductions are. The highest value for the oxidation, the highest value for the reduction, that determines what can happen. Now, in the case of this is a spontaneous reaction, we can tell because it has positive voltage, right? If you're just mixing some solids in with ions, you should be able to figure out what is reduced and what isn't based on its position on a reduction table. Remember, the higher anything is on a reductions table, the more likely it is to be reduced. Okay? So in this case, the potassium and the zinc were below iron, so it's more likely that iron will stay reduced than potassium and zinc becoming reduced. Whereas silver and copper were above iron, so those are immediately reduced upon contact. And the one that's higher up is the one that will happen first. In this case, silver happened first. An electrolytic cell is one that requires outside power to operate. So in electroplating, what you're doing is you're getting a metal to become reduced onto the surface of an object. This requires energy because you have to replenish the metal ions in solution. That is why the oxidation and the reduction are just reverse equations of each other, because we have to oxidize gold so that gold can be in solution so that it can be oxidized, or I'm sorry, it can be reduced. When you electrolyze water, you must recognize that water is a possible participant for both oxidation and reduction, right? Its value is on the chart. When you look at the chart, the reduction potential is written plainly from left to right, but if it's the oxidation of water you need to find, it's written in reverse on your chart. We need to be able to solve for the energy based on its potential, right? So potential multiplied by the charge gives you joules. You need to know what a Faraday is the relationship between moles of electrons and coulombs. And amperage, right, is the rate. So it's your amount of charge per unit time, which is, coulombs per second. And we use that information to help us figure out the mass of something that's going to be plated, right? But we can also use the mass to figure out how long it took or how long it's going to take. And then lastly, we now are able to relate voltage, free energy, and the equilibrium constant. And so you could use any combination of these reactions to solve for the variable that you need. Really they're just, some of these are just permutations of another. The equations are going to be on your formula sheet, on your AP formula sheet, particularly this one, right? And this one, and this one. Those are on your AP formula sheet. All right, so, okay. That's enough of that. 3 minutes to spare. Okay.